This is Lecture 14 of Soil Mechanics, Retaining Walls and Lateral Earth Pressure Theories. And for some reason, students find this topic something of a mystery, and I'm not really sure why. I think it has to do with what they've been exposed to up to now. Soil mechanics is, generally speaking, most students' first exposure to 2 or 3 dimensional mechanics of materials. And as a result of that, it tends to, there are many things that happen in 2 and 3 dimensions that nobody worries about in 1 dimension. And one of those is the fact that if you have stresses in one direction, generally speaking, it will generate stresses and or deflections in another. And that's basically what happens with retaining walls and lateral earth pressure theory. Nevertheless, in spite of that, lateral earth pressure theory is something that is too important to ignore because there are many places where we actually experience this, particularly with retaining walls, but there are other places as well. So let's begin. Elevation changes are an unavoidable part of site development, and it's particularly true in a place like we're at, where you have it's fairly hilly. But elevation changes can also be required in places which are perfectly flat. They can either result in changes in the land elevation, and those changes can either be part of the site to start with or something that we need to have. For example, an overpass. If you have an overpass, you have 2 roadways at 2 different elevations, and you're going to have an elevation change in the site. A land-water boundary, dock, wharf, pier, seawall, those things. And there's normally 2 ways that we deal with them. One of them is earth slopes, unreinforced and reinforced earth slopes. And we just talked about unreinforced earth slopes. And we got a little bit into reinforced, but not much. And retaining walls. Like I said, in slope stability, if we could go through life with strictly unreinforced slopes, that would be the easiest. But the problem with earth slopes, as you can see from that little illustration, is that they take up a lot of real estate. And frequently we don't have that kind of real estate to deal with. And as we get more into urban development and development in areas which have already seen development and have other structures, and we don't have the real estate or the right-of-way, we have to do retaining walls. There are 2 basic categories of retaining walls. We're going to come back to this again in foundations. One of them are the gravity walls, masonry, stone, gabbing, etc. And the other one are in situ walls. Now I'm going to probably save the distinction of that for later. We got some more basic things we need to talk about first. Let's start with talking about lateral earth pressure coefficients. And I think this is where there are several distinctions and categories which we have that that are sometimes hard to break down. And those are the conditions of lateral earth pressure and the theories by which we estimate what that lateral earth pressure is. But before we do either one of them, we need to make a fundamental definition. And that is the lateral earth pressure. If we have a sample and we put it into compression, depending upon what material it is and how much stress we put on it, force we put on it, it's going to bulge at the sides. If we contain that, if we try to put that in some kind of container, then depending on the container, we're going to trap that, and we're going to develop stress as that mass attempts to deflect laterally, and it's the volume which is displaced by us pushing down on it is going to want to move out. When it can't, then stress results. The ratio of, normally speaking, in soils, we load them vertically. In other words, the stresses that we put into the soils are vertical, and we've talked about vertical stress. We've talked about vertical effective stress, which is what we start with. We talk about induced stress. That's what we did with Busanesque 2-to-1, and we induce stress. And then, but however, when we do that, when we have a vertical stress, we induce a lateral stress or a horizontal stress in the soil. The ratio of those two, no matter how we do it, is referred to as the lateral earth pressure coefficient. And those of you who are thinking about mechanics of materials may think about the fact that there are other ways that other ways of measuring that Poisson's ratio, and we're going to talk about the relationship with Poisson's ratio in limited conditions. But basically, without having to go into any other details, you must understand that the K, lateral pressure coefficient, is simply equal to the horizontal stress over the vertical stress. And I say horizontal effective stress over vertical effective stress if we're only dealing with the soil stresses themselves. The self-induced soil stress, the self-weight of the soil, as Freud would put it. Then that's effective stress is it. But that can also be induced stresses by our activity, and the stuff that we do also induces lateral stresses, and we're going to see that in great detail in just a minute. All right, we're going to talk now about the conditions of the lateral earth pressure coefficient. There are 3 of them, which we're going to discuss. The first is the at-rest condition. The at-rest condition is basically the condition that takes place when you have either the self-weight of the soil or induced stress or a combination thereof acting vertically, and the horizontal stresses take place in an environment where there is no possible horizontal movement. In other words, the stresses are trapped, or somehow trapped. And the classic way that they're trapped is in the A diagram, 2-19A. We have a semi-infinite soil mass. We induce, or actually stresses are induced by the self-weight of the soil to start with, and then we can add to those later. But there's nowhere for the soil to go. Why? Because it's a semi-infinite soil mass, and whatever is next to it doesn't have, you can move that, but then it doesn't really have much of a place to go. It'll move a little bit, but ultimately the whole system, but eventually it's going to go, at least in theory it never goes to zero, but eventually it's going to die out because there's no place for it to go. And as a result, that condition is called the at-rest condition. An at-rest condition also can take place when you have a rigid wall. Now, a rigid wall is one of those great engineering concepts that really doesn't exist in reality, but we say that. If we have a wall that is very unyielding and doesn't move, sometimes it will do at rest, but not very often. Most of the time, at rest is principally with soils which are actually trapped in the semi-infinite mass, and they don't go anywhere unless they go very little. There's no place for them to really much to go. Now that's the at-rest condition. The at-rest condition is important not as much for lateral earth pressures as it is for the estimation when you're talking about if I do a vertical stress in the soil mass, what will the horizontal stress look like without any retaining wall around? That's where the at-rest condition is most of the time experienced. When we get to a wall, if I induce a stress in a vertical stress, and the horizontal stress is pushing against the wall, and the wall is say not, there's nothing on the other side of resistance, or the resistance is minimal, then what's going to happen is the wall is going to move away from the horizontal stress that I'm inducing, that delta A in diagram C. And that's referred to as an active condition, when the wall moves away from it. And I mean, these wall movements are not particularly large, but they're movements nonetheless. On the other hand, in some cases, and active cases, by the way, are what we most normally think about when we think about, retaining wall holding back soil. Most of the time, when the soil is pressed down, the lateral earth pressure or attempt to push the wall, basically the wall tends to kind of be pushed away from it, or runs away, so to speak, from it. And those are active pressures. On the other hand, we have certain situations where the wall decides it's not going to take it anymore, it's going to fight back. It's going to actually push against the soil. Those conditions are called passive conditions, where the wall actually pushes back against, where the soil receives the push. And those conditions are particularly important in walls where balancing soil pressures is the way the wall stays up, like a sheet piling. Active condition is generally the lower state of lateral earth pressure. Passive condition is generally the higher state of lateral earth pressure. The effect of wall movement can be seen. You see that diagram. I've presented other versions of this over the years. We have a situation where if the wall starts in a certain way, and so it's got a height h, which you need to understand that. And then they've got this deflection y at the top. If y is to the left, in other words, the wall is moving away from the soil, then we have active. And the ratio of the horizontal to the vertical stress K tends to be low. And that particular chart is based on a certain test. Those values can be different. But the relative state of difference, and we're going to see this in action here just shortly, that's an active state. The state where the wall doesn't move at all, where y is basically 0, is the at-rest state, the K0. And then passive state, where the wall moves into the soil, is called the passive state, KP, and it's a very high ratio. In other words, at that point, we get an interesting situation where the horizontal stresses are greater than the vertical stresses. Generally speaking, passive state, the at-rest states in the middle, the passive states are higher and the active states are lower in terms of the ratio of horizontal to vertical stress. K is not restricted to being less than 1. And you see that there are various values that have come up depending upon the magnitude of the wall. That's going to become more important in foundations when we get into software situations. Traditionally in soil mechanics and traditionally in retaining wall design, the classical ways of doing it basically assume that the state of soil stress is either active or passive, or in the rare case at rest, and that's it. But what you see in this chart is actually it's a continuum. You start at a 0 point, you get movement away from the wall, the active coefficient varies until it reaches some kind of Well, equilibrium or failure actually is what it is. Or as it reaches some sort of where it's not going to change anymore. But that's usually at the failure state. And on the other hand, the passive is the same way. You reach a point where you don't get the ratio of horizontal vertical just basically steadies itself out. And those values for that are actually measured in terms of the ratio of the wall rotation at the top, particularly, versus the height, the Y over H ratio. And typical Y over H ratios are given in that little table down there. Those will become more important when we get to foundations. For the moment, let's stick with the concept that it's kind of like the same thing with the failure function. And they're actually related. The failure function tells us that there are varying degrees of soil, that the soil will deflect up to the point where it experiences failure, but that those states are interesting to us up to a point when we failure. But classically in soil mechanics, we teach that all we care about is where it fails. Failure function is an important concept, and the same thing here. We're just going to focus on the states at which we have either failure in the case of active or passive, where the Ka reaches some kind of equilibrium value, or I call it equilibrium. That's not entirely accurate. Where it reaches it settles out to a certain value is probably the best way to put it. At failure, rather than worry about the intermediate stuff, we'll come back to later. Let's start with at-rest lateral earth coefficients. At-rest lateral earth pressure coefficient, K0, which also exists in the soil mass. In fact, principally exists in soil mass. The at-rest condition primarily describes conditions with a semi-infinite soil mass and level surface. They can also describe a wall which is quote-unquote unyielding. And some of you have probably figured out that there is really no such thing, that walls are going to move some, it doesn't matter how much. So, how do we estimate? There's a lot of, Vroit spends a lot of time on this subject, and he goes into theory of elasticity and whatnot, but Vroit eventually admits that finding out the lateral earth pressure coefficient and Poisson's ratio, for that matter, for soils, can be a very tricky proposition, and has been for a long time. The best estimate we have, and it doesn't have much theoretical basis, and it doesn't really have, it really doesn't have any, is Jackie's equation. Jackie was a Hungarian who came up with this right towards the end of World War II. And basically, K0 is equal to 1 minus sine phi. And you'll probably recognize that from the previous discussion of the slope stability problem, where it asks for the neutral earth pressure coefficient. And that's Jackie's equation, is the at-rest or neutral earth pressure coefficient. And that's the formula I gave you. Now I'm explained it. It's held up pretty well. Attempts to try to get fancy about it have not done very well. The only modification you see commonly for Jackie's equation is the modification for over-consolidated soils, where they add this thing at the end of the sine phi times the over-consolidation ratio or the pre-consolidation ratio. And we talked about that in consolidation settlement to the sine phi exponent. In spite of the theoretical weaknesses or lack of it thereof, Jackie's equation is a good estimate as we have for general purposes. Obviously, in specific situations, we can get try to get a little more precise, if not necessarily accurate. But Jackie's will get the job done in situations like that. If we decide to put together Jackie's equations with elastic theory, again, we go back to our elastic perfectly plastic model. In the elastic region, we can actually apply a theory of elasticity to that, and Freud does it in this particular. Now notice very carefully what he does, and this is important. First thing, in a medium of large horizontal extent, that's semi-infinite medium, we can expect that all of the horizontal stresses will be the same no matter which direction they're in. No matter how we set sigma x and sigma y, or how we set x and y axes for that matter, they're going to be the same. We can also assume that the strains are zero in those directions because it's a self-confining medium. There's nowhere where the soil can really go. You've got an semi-infinite soil mass basically containing itself. So we say those are zero. Once we apply those to the normal theory of elasticity equations, and you'll see those in advanced mechanics and materials course, you end up with the relationship between the vertical stresses and the horizontal. The horizontal stresses over the vertical stresses are equal to nu, which is Poisson's ratio over 1 minus nu. If Poisson's ratio is between 0 and a half, at half, of course, those of you who remember from, I think I've probably mentioned this in Fluids Lab, but I'll mention it here again. At 0.5, we have a fluid. That is the highest value of Poisson's ratio, and the value of K varies from 0 to 1. One interesting aside in finite element analysis, because of the way the constitutive equations are set up, Poisson's ratio 0.5 is a singularity, which leads to some interesting. And really, soils, as I've mentioned, are kind of an intermediate material between true engineering solids and fluids. In a sense, they are. And some soils, like very soft clays, may act as fluids, but to get down to the brass tacks of it, they're probably, we say in many cases, and we use the nu is equal to 0.5 for a lot of simplification of Boussinesq equations and whatnot, but the reality is that's sort of an extreme case that we don't really see, unless you've got a real live fluid. So that's the relationship, and you can, if you take that relationship and apply it to Jackie's equation, you get values for phi and nu. Actually, you can relate the two, which is a very interesting concept. All right, let's take the retaining wall of sun. Let's assume that it's truly unyielding. We have finally searched the world and found the unyielding wall. We have a dry cohesionless backfill, gamma 120 PCF, and phi is equal to 30, the internal friction angle. If we look at this, the height is 20 feet. If we look at this diagram, and if you were to draw a P-naught diagram of this, you would get a linearly increasing pressure against the wall if K is constant. You get literally, let me back up. I'm kind of got ahead of myself. You will get a linearly increasing effective stress. So it's dry, there's no water to mess things up. And if you do that, then you've got several things. If K is constant, if the relationship between the horizontal and vertical stresses are constant for that soil, then you will get a linearly increasing stress and pressure against the wall. If you were then to take that pressure gradient and integrate it and concentrate it into a resultant, which is a single force that replaces a distributed one, you'll get that P0. And that P0 is located at a height of h/3 from the bottom of the wall, and believe it or not, 2h/3 from the top of the wall. So that's the results. We're going to be dealing in resultants, lots of resultants. Geotech engineers love resultants. Traditionally, in hand calculations, they're the way we use to eliminate a lot of the problems that come up using distributed forces. And when we can use them, we do use them. Now, in some cases, the results are different. But for overall, if we want to know the total force the soil exerts against that wall, the resultant is the answer we're looking for. All right. The first thing we do in any lateral earth pressure problem is compute the lateral earth pressure coefficient. Since I stated to you that the at-rest earth pressure coefficient is 1 minus sine phi, it's normally consolidated. I just simply plug and chug. I gave you phi, so K0 is 1 minus sine of 30, which is equal to a half. K0 being a half, then the next thing is the effective wall force. Now, the P0 over B notation represents the fact that all of these are per unit length of wall. And this is another source of confusion. We've talked about this since the days of permeability when we talked about our per unit length of water flow. This is the per unit length of force. And we're going to see this over and over again because what we're doing is we're trying to represent a three-dimensional problem in 2 dimensions as long as the third dimension, in and out of the board or the screen or whatever, doesn't change. So with that in mind, gamma, and that's equal to gamma z squared. And z squared, by the way, I know that I probably should have put h squared. That's probably where some confusion. But z squared at any point, in other words, at any point along the wall, the force from the top of the wall down to that point is equal to z squared, to where at any point z. If that point z happens to be the total height of the wall, then z1 squared is h squared, which is why you'll notice I substituted 20 in there. So gamma z squared K0 over 2, and I just simply plug and chug. And what I end up with, and that should be 12,000 pounds per foot of wall, not foot pounds. It's not a moment. 12,000 pounds per foot of wall, or 12 kips per foot of wall. And the height of where that resultant is located is equal to 20 over 3 or 6.67 feet from the bottom. And that height, by the way, if you've got a triangular distribution, it doesn't matter which theory you're using, that height isn't changing. If you have a uniform distribution of pressure, which you do with surcharges and that kind of thing, then it's going to be it's going to be the height over 2. So that's the first that's the first thing. The at-rest pressure example gives us this result. We can compute for an unyielding wall the amount of force against the wall. Now we're going to transition from just earth pressure conditions into theories. We've talked about the active and passive conditions. Now we're going to talk about the theories. With at-rest conditions, Jackie's equation is about all we're going to talk about. With earth pressure theories, we're going to talk about three different earth pressure theories for each condition: Rankine, Coulomb, and log spiral. Coulomb was the first one, actually. And Coulomb assumes basically that there is a wedge between the soil. I'm going to get into more detail about what this looks like in a minute. There's a wedge between the wall, which is on the left, and that slope surface is a failure surface. In other words, the way it applies downward. We actually saw this, a preview of this we're talking about upper bound theory. And it goes down. The weight essentially wants to drive downward, and if it works along a wedge, it's going to try to push the wall outward, and the wall runs away from that. Coulomb originally is the same one. It's the same person that came up with the electric charge. Electric charge unit is named after him. Came up with this while he was on a project in the French West Indies, which is proof that you can do more when you're down in the Caribbean than just have a vacation. And so he came up with that. He includes friction between the wall and the soil, and of course obviously the soil in itself has friction, but there's also friction between the wall and the soil. He includes the effects of that. Rankine was coming up with the Scotsman that came up with that, and there are two major differences between Rankine and Coulomb. Rankine can be derived for level backfill. Now we talk about, that's another term that I'm going to get into, is level versus sloping backfill. We'll talk about that in a minute. But for level backfill, or a level soil surface, let's just put it that way, Rankine theory can line up with Mohr Coulomb perfectly. But basically, from the standpoint relative to Coulomb, Rankine leaves out the effect of wall friction, of soil friction on the wall. And as a result, Rankine theory is more conservative. In fact, of the three theories you're looking at, it's the most conservative. Rankine theory can be derived the same as Coulomb if we leave the delta out. They leave the friction out. It can also be derived again from Mohr Coulomb. So either way, you get the same result. Notice that in both cases for Rankine and Coulomb, if we push, particularly it's easier to see it with Coulomb, instead of the weight of the soil pushing against the wall in Coulomb is fighting back. And we're going to see that more clear in a second. Log spiral theory is the last one. And log spiral theory basically throws out the idea that the failure surface is planar. Notice in Coulomb that slope surface, failure surface is planar. In other words, it's straight. Log spiral says, no, that's not true. It's actually more of a log spiral. And we're going to come back to this with a vengeance when we get to bearing capacity problems, but it assumes it's different. And the log spiral is very useful, and it's got an important place, but the computations are a little bit more complicated with log spiral. All right, let's start with Rankine. I think probably this is as good a place to stop for a second and discuss about what Rankine is all about. Rankine basically assumes, and this is based on Verreut's little app that he has, basically assumes that we can either come up to Rankine based upon, with level surfaces, we can assume that it jives perfectly with Mohr Coulomb theory. And basically what we're doing, particularly, is we start at a certain stress state. And either for active, we expand it or contract it with passive. And we come up with a lateral earth pressure coefficient, and that can be based strictly on Mohr Coulomb theory. You remember some of the stuff we looked at earlier about that. With Rankine, if we have frictional resistance and no cohesion on it, a purely cohesionless soil, and a level backfill, level surface, the Ka is equal to the tangent squared of 45 minus phi over 2. Keep in mind, if you do this in a spreadsheet, spreadsheets like radians for angles, not degrees. And then after that, I'm looking at the column to the left. The sigma A is equal to Ka Z, and that's basically all that says is that's the active pressure at any point along the wall. At any point Z along the wall, and my notation here is a little clearer than it was before. Ka sigma Z, it's a little clearer. And then the total pressure is, we integrate the whole thing to the Ka gamma H squared over 2, which I just looked at with at rest theory. Again, it's the same. That part, once you determine, the beauty of using lateral earth pressure coefficients instead of, say, trying to analyze the wedge, is that the wedge, the wedge can be a little more complicated. Once you get a single number for the earth pressure coefficient, then you're done. Passive, that box D, then is tangent of 40 squared. Tangent squared 45. I'm not sure if I left the squared out in the active, but it's definitely there. Tangent squared of 45 minus V over 2 is active. Tangent squared of 45 plus V over 2 is passive. But once you've established that, the computation of the actual pressures and forces is the same. You'll notice that it shows the movement with the active in A. The movement is away from the soil, like dash line, and the movement is towards the soil with passive. And that's the difference. If we throw in cohesion, things get a little weird. Because, and the reason why they get weird, is if we have a purely cohesive soil, then we have a height of tension zone. If you recall from lower and upper bound theory, if we dig down and we excavate in a cohesive soil, we're going to get up to a point, up to a certain height. You are able to say, you are able to have a vertical cut. Well, if you were to, and there's good reasons not to do this, by the way, if you were to put a retaining wall in a purely cohesive soil, well, sometimes you're forced to do it, in which case you have to make provisions for the drainage, and we'll talk about that later. But if you were to have the tension, if you were to put that wall, and you were to basically excavate and then put the wall in, or whatever, or however you do it, you put the wall in, basically a purely cohesive soil will think that it's, from up down to a certain point, will be able to stand on its own. Well, it's a high of the tension. The theory tells me it's supposed to be in tension. The reality tells me that, no, it's not. It's not going to be in tension. And so, it really just, so you've got a part of that which is basically free. In other words, the wall just stands there, and the soil just stands there behind it, and they just kind of sit there and look at each other down to a certain height, Z naught. And the Z naught is equal to 2C over gamma. And I encourage you to go back and look at your material on upper and lower bound, because you will realize that basically the Z naught assumes lower bound conditions. In other words, in retaining wall, we take the more conservative approach. We say, well, and there's good reasons to do that. If we have a cohesive soil, we're going to assume the lower bound solution. That's a place for a lower bound solution. And then the sigma A and the PA follow from that, and the passive, it's pretty much the same kind of thing. The only difference is that in passive, it interacts with the soil a little differently, as you can see. If you combine the two, you still have that Z naught, but the only problem is that the Z naught is modified by the existence of internal friction in the soil. That's what that's all about. And that is, by the way, a practical application of the vertical cut theory we went through, which some of you were scratching your head thinking, why is he wasting our time on this? Now you know. Okay, from the standpoint of Mohr Circle, we developed active pressures this way. We start with a sigma 1, which is the pressure with vertical pressure. And basically what we do is the wall runs away. And as the wall runs away, and you can see there another range of distances to develop. In other words, what you're looking at over there is the distance basically the y over h ratio. The y, the 0.001, 0.00, the y over h ratio we looked at earlier. You can use that to estimate, somewhere in that range of wall deflection at the top, we achieve full active earth pressure. Basically what happens is the wall runs away and the confined pressure drops. And it drops to the point where we get failure in the soil. And that is, and that's one way of looking at it. Of course, the other way is the wedge method, which Coulomb uses. But in Rankine, this is the way it is. And you simply the wall runs away until it achieves a low enough. In other words, you can see that as you keep decreasing from at-rest conditions on down, the confining pressure, in other words, as the wall runs away, the confining pressures drop to the point, and the failure function, well, it increases because it's negative when things are going when inside the envelope, to the point where the failure function hits 0, then you have failure, wall failure. I want to also, before I get into the example problem, I probably should use this little diagram. And it says Coulomb active, but Rankine. Notice that, watch carefully, as the wall goes away from the soil and the wedge goes down, and because the wall is going away, the Ka will be lower than the Kp. But that's active. All right. Okay. Let's take an example. Retaining wall is shown. Find the PA from active conditions. Same problem we had before. Notice now we're throwing in an alpha A. That is the failure surface. Rankine active wedge. Like I said, with Rankine theory, you can derive the equations either from more Coulomb failure or from active. You get the same result. That's nice. Okay, compute the active earth pressure coefficient. We get that in the chart. We're assuming level backfill. We're assuming purely cohesionless conditions. So the K is equal to tension squared of 45 minus P over 2. And I substitute into that, and that doesn't look very nice. But I come up with an effective wall force. And again, this is the same plan. You'll notice the 120 is the same. The wall height's the same. Everything this is the same except for Ka. There's a slight typo right here. This should be 1 over. For some reason, these equations have lost their slashes. So we have 1, that should be 1/3 there instead of 13. Should be 1/3 over 2. And I end up with 8 kips per foot, which, if you remember, is lower than the at-rest condition, which makes sense from what we discussed previously. Passive earth pressures are developed differently. They assume that something is pushing into the wall. You see but they're just opposite. What happens is we start out with a vertical pressure, and the horizontal pressure increases until we get failure. In the other one, the horizontal pressure decreased till we got failure. In this case, the increase. And by the way, let's look at Roy's little diagram for passive pressures. And it goes like this. Notice that now the wall is going into the soil and is pushing the wedge upward. And to push the wedge upward, it induces failure by pushing upward, at which point it doesn't push up anymore. I would strongly suggest that you get this little application, which is on my website, download it and play with it. There's all kinds of stuff in it that you will find useful. Okay, Rankine passive pressure example. Same thing, alpha P, you've got wedge failure. And I'm not really pushing very hard on computing alpha. But gamma T is the same, phi is the same, the HP the pad is the same, the height of the wall is the same. Here we go. The only difference, though, is now the passive earth pressure coefficient is equal to tangent squared root of 45 plus phi over 2. Level backfill, purely cohesion in the soil. Effective wall force, and so you plug and chug, you get Kp is equal to 3. By the way, Rankine active and passive earth pressure coefficients for the level backfill and the cohesion of soils are reciprocal for each other. So if you remember, Ka was 1/3, Kp is 3. This also applies to other angles. I simply substitute. This time I've got 3 instead of a third here, and I get 72 kips per foot. And that's the summary of the at-rest, and we're also going to do, and that's the summary of all of them. You'll notice we started at 12,000 pounds at rest. We went down to 8,000 pounds, that should be pounds per foot, for passive, and 72,000 pounds per foot for passive. And that pretty much corresponds with the theory that we're presented with here. If, as I noted in slope stability, not all backfill is level. If we have a slope coming up from the wall, we will have an angle beta. How do we incorporate that? A lot of things change. The failure surface is maybe a little different. The direction of the force is different. Instead of having a purely horizontal force, you've got a horizontal and vertical component with a force. Things change. The way we take that into consideration, however, is by changing the earth pressure coefficient instead of changing the theory. Just as an aside, inclined backfills usually end somewhere. If they don't end too close to the wall, then you can pretty much assume that it's inclined for the duration, and you can compute your earth pressure coefficients that way. If it comes up and then flattens out or something like that, it's called broken backfill. And to solve it, you either need to use a finite element, or traditionally what we've used is something called trial wedge. And trial wedge is aptly named. It's a fairly tedious procedure to compute forces on a wall. These are if I include a beta greater than 0, this is the Ka and Kp for Rankine theory only. It does not apply to Coulomb theory. You'll note if I put beta equals 0, these will reduce to your active and passive Rankine conditions. All right, beta equals 0, they're the same. Now, look that way. One of the things that earth pressure theories has been over the years has been a attempt for geotech engineers to show their trigonometric skills. And so a lot of times the formulas will not look the same on first glance, but if you apply a little trigonometry, you will get the same result. Before I move on to Coulomb theory, it probably would be good to talk a little bit about walls with cohesive backfill. And in a previous slide, I actually looked at that with respect to the basically the tension zone or the no stress zone and that kind of thing. But I want to go back to it. Ideally, retaining walls should have cohesionless backfill. In some cases, cohesive backfill is unavoidable, especially if you're in an area where that's the predominant soil. The problem with cohesive backfills is primarily, number one is poor drainage. Creep and expansiveness are problems depending on the type of cohesive soil you have, but poor drainage is number one. And in fact, it is in some ways the leading cause of retaining wall failure is poor drainage. Unfortunately, from a theoretical standpoint, a lot of the retaining wall theory was developed with cohesionless soils, and cohesive soils are kind of an add-on to it, and not a very graceful one at that. With Rankine, it holds together, and I'm going to show you this. If you look at Mohr Circle, and you look at, I said if you have level backfill, that Mohr Coulomb failure theory and Rankine theory basically coincide with level backfill. That is also true if you extend it to cohesive soils or mixed soils. And you see that in the case of this Mohr Circle, that the sigma 1 and sigma 3, basically what that's saying is that the first one is the passive case, the wall is driving it, and the second was the active case, the overburden is driving it, depending upon whether sigma 1 and sigma 3 being the two principal stresses. And in kind of informal way, we're saying that one of those directions is the sigma 1 and one of those directions is the sigma 3. And if you take out the first term of both of those equations are the cohesionless active and passive pressures. And you'll notice, again, I said that lateral pressure theory is a chance for geotechs to show off their prowess in trigonometry. And you see that here. You've got the tangent. You'll recognize the tangent squared pi over 4 plus phi over 2. And that's, by the way, in well, that by the way is the formula in radians. It's equal to 1 plus sine phi over 1 minus sine phi. And you'll notice that Ka is 1 minus sine phi 1 plus. I said those two were reciprocals. They are. For cohesionless soils in Rankine theory, level backfill, Ka and Kp are reciprocals of each other. Keep that in mind. It's a very handy little rule. Tangents, and you'll notice that it can be expressed differently. The second term is the cohesion term for that, and so therefore we can sort of add that onto it. And if you'll compare those and do some derivations with a few slides back where we actually get into that, you'll see that they are in fact the same. This one and that formula are basically the same one. We talked about the tension zone. I don't know why they call it tension. It's really the no stress zone is what it is. The tension zone and whatnot. You'll see that those equations are the same. So with an overburden driving the active case, if Ka is defined as the level backfill cohesionless, then the sigma 3 is equal to the lateral pressure is equal to the effective stress times the active earth pressure for cohesionless minus 2 times the cohesion times that pressure times that square root of that coefficient. Passive is just the reverse. the driving stress, the sigma 1, in that case, the principal stress is actually horizontal for passive cases. It's equal to sigma phi naught, the effective stress, times that passive earth pressure coefficient for level backfill in cohesionless case, plus 2c times that. In other words, the cohesion actually increases that horizontal stress for the passive case. Again, you see I reproduced that. You need to go back and look at where I presented it before. I don't mind repeating myself if I have to. Rankine equations are valid if you don't take wall-soil friction into account. That is generally speaking, that is a conservative assumption. Most of the time we can actually get a less conservative result if we take that into account. And many times if we're not sure of it, we're better off not doing that. In fact, there are some types of walls where I would not recommend anything but Rankine being used. Principal of those would be sheet pile walls made out of very smooth material, such as vinyl and pultruded fiberglass, and to a lesser extent aluminum. I would not use anything but Rankine on those walls like that. They're just not there, and there are other reasons for that as well, but that's the principle. Do not take into consideration soil above that critical height. That critical height again is based on lower bound theory, and these the equations they're the same as the ones before, include whatever the Z naught is actually affected by the presence of friction of frictional effects in the soil. Does not take into account sloping walls. Sloping walls are a whole different, have different considerations. Sloping wall, there are some types of walls which are sloping. There are many of them which are not. And for practical problems, you can use the equations as they appear in both of your books. Actually, there's two in either one of them. I'm going to make a comment on Veroit's versus the Soils and Foundations Handbook. I would, as the general rule, use the Soil and Foundations Handbook formulation. Particularly when we get to Coulomb. That is, of course, when we include all kinds of stuff with Coulomb. One, obviously, beta, the sloping backfill is included. But theta is the wall angle. In this particular case, I want you to draw your attention to the diagrams on the right before I get into the formulas. Theta is the angle away from the vertical on a wall. Now, sometimes you will see the angle given as, I think Veroit uses an alpha, is an angle from the horizontal. In which case, for a vertical wall would have an angle from the horizontal of 90 degrees, an angle from the vertical of 0. And you see the effect of friction. The little delta changes the angle of the force, of the passive force and the active force. And the formula for each of those is quite a bit more complicated. Quite a bit more. You see Ka for the active case and Kp for the passive case. Now I'm going to make a statement. You need to listen to it carefully. And it's not just the fact there are two books do it differently because one comes from Europe and one comes from the United States. Textbooks and reference books in general have, the formulas for Coulomb earth pressure coefficients, particularly Coulomb. Rankine's also include, particularly Coulomb. There are all kinds of different ways of handling this problem. For example, in U.S. usage, we normally stick with positive values of delta. Beta and theta can go either way. And in fact, that's why your soils and foundations. Varroy use a lot of different. If you use Varroy's formula, you need to become familiar with his sign conventions for delta and for alpha and a lot of other things. Personally, I think you need to stick with what you're looking at. You'll get be a lot better off. The height of the wall is the vertical distance from the top of the wall to its base, not the length of the wall. If the wall is not vertical, that's going to be different. So keep that in mind. Now, however, the most important thing I need to point out is the first one. Coulomb passive earth pressure coefficients tend to be very unconservative. Very unconservative. And in fact, the usual way of, not the usual, one way of dealing with that, and one that's commonly used in the U.S., is the use of Coulomb for active and log spiral for passive. That's the AASHTO combination. That's a common way of getting around. There are other ways of doing it. If you use Rankine overall, you don't have that, but it's a little more. It's more conservative. The AASHTO combination, and you'll hear me talk about this both in this course and the next one, says that the Coulomb wall that uses Coulomb for the active pressures ignores it, gets away from this problem, and log spiral for the passive. These are typical values of wall friction, either expressed as an angle in degrees or a tangent of delta. Either way, you can do it either way. This table came from DM7, and it's been around a long time. All right, let's take an example of Coulomb theory. Given a wall as shown above, find the Ka and Kp and Pa and Pp of the passive, both the forces on the active or passive, whether it's an active or passive case. You've got one of each. So first, you compute the Coulomb active pressure earth pressure coefficient. Ka is equal to, and you just simply substitute into those equations, you plug and chug, you get a Ka of 0.3465. You compute the total wall force exactly. Once you've computed the Ka, the rest of the formula is the same as we talked about with Rankine. And you get Pa of 8316 pounds per foot of wall. On the Coulombs, on the passive side, the Kp computes to 4.02, something like that. You substitute in, and that passive pressure is mislabeled in there. It should be pp rather than pa. Is 96,470 pounds per foot of wall. You'll notice that that's large. That is larger. In fact, that again, Coulomb is not as conservative, and in the case of passive, it really drifts into being less than conservative than you have with active. Up to now, we've assumed the failure surface of the wedge behind the wall to be planar or linear. Actually, planar is more accurate. However, that doesn't always work out. A more realistic way of modeling it is to use the log spiral. And I want to talk more about log spirals when we get to foundations, but as you can see, that failure surface is different, especially for the passive case. The problem, the drawback to using log spiral failure is that, and I'm always one trying to dig to find numerical solutions, and I have not found one yet. For the moment, we'll have to use charts for this. It is especially useful to address the weakness, and I'm going to, let's see, show you that weakness. If you look on the left, if delta is equal to phi over 2, if delta is vertical wall, level backfill, pretty typical situation, Coulomb and log spiral don't vary that much. until you get to very high friction angles. And really, by the time you're 40, there are not many soils that go 40 degrees friction. Not many. You get, unless you've got some very, angular gravel. That's about it. However, if the friction angle increases to delta is equal to phi, look at the difference. At 35 degrees, let's forget about 40 degrees for a minute. For Coulomb, the KP is somewhere in the range of 22 degrees. 22, excuse me, not 22 degrees, 22. Whereas the log spiral is 10. That's over a factor of 2, and that can make a big difference in the wall design. The charts given in the Soils and Foundations Handbook are used in this way, and they actually have some nice little examples of them. There are 2 of them. And basically on the one on the left assumes that the backfill is horizontal, but the wall is not. There's an angle in there. And of course it also includes the zero angle. So if you've got a level backfill, you would use the chart on the left. And then the chart on the right, it is different in the fact that it assumes the wall is vertical, but the backfill isn't. And so therefore you're dealing with 2 different cases. It would be nice to be able to, and the 2 charts actually meet in their results, or should meet in their results, when you've got level backfill and a vertical wall, theta is equal to 0. Notice carefully that those little diagrams at the top have have a sign convention for everything. In other words, the beta has a plus sign convention, the theta has a plus and minus sign convention. Always, always, always look at your sign convention when you're doing it. When you're actually solving a problem, always make sure you understand the sign convention, particularly with Coulomb and log spiral. You don't, you're going to get in trouble. As far as the change of reduction factors, as far as that is concerned, we're going to talk about, there are 2, each of them have examples. And generally speaking, we have an example, for example, phi is 30, theta is minus 10. That would, and say delta over phi is equal to minus 0.6, which is the normal. Most of the time it's going to be negative for these charts. And these charts are actually originally, as the ply were developed in France, and that's why you see the delta over phi being negative. If you just look at the chart at 30 and delta over and theta is equal to, don't forget, it's minus 10. In other words, it's actually, the wall is actually leaning from the top, it's actually going left. You go up to theta minus 10, and you end up with something about, let's see, about 0.811 according to this. No, excuse me, 8.2, excuse me, I'm sorry. 30 comes up, you hit minus 15, somewhere in the middle is 8.2, somewhere around right through here. Okay, that's how you figure that. That's where that comes from. Then, since delta over phi is equal to minus 0.6, and since phi is equal to 30 degrees, the reduction factor you then apply is 0.811. That goes there. That's where that comes from. Here, you multiply it to, you get 6.65. And that's how you use these charts. because I'm not going to get into the active charge for these, because most of the time in our practice we don't use them. We would use either Coulomb or Rankine. All right, before I get into go any further, I want to talk about the effective groundwater, because this is an important point. I said that you compute the pressure along the side along a retaining wall by multiplying the effective stress of the effective stress of the soil at the point below the surface times the active or passive earth pressure coefficients, depending on whether you have active or passive earth pressure conditions involved. And so that is true, except now in the presence of water. Now, obviously, we've known from effective stress is that and once you get past the water table, the buoyant effects kick in, and the effective stress does not increase as rapidly. And as long as there's water on both sides of the wall and that water level is the same, that holds. That's pretty much it. However, if you have a situation like you're looking at here, where there's no water on the left side, you have to add back the unbalanced hydrostatic force of the water on the soil side of the wall that is not compensated for on the other side. And probably the easiest way to illustrate this is to use an example, which is from your Soils and Foundations handbook. So, for example, I have this. It has level, it has a sloping backfill. It has, and for those of you who are tired of have criticized problems where the unit weight is the same on both sides of the water table, well, guess what? It's not here. So now you should be happy. I have a water 6 feet below the surface with a groundwater table, and 12 feet is the bottom of the wall. But this is important. But there is no groundwater. There is no water on what I call the excavation side of the wall. There's no water over here, so you've got unbalanced force. How does that work? We first start by computing the effective lateral pressures, and this is a nice illustration of that in general. First, I compute Ka. The soil has the same phi in both cases, and the beta is obviously the same. So the Ka is all the same up and down the wall. It's 0.374, and we're using Coulomb theory. And I would strongly suggest that you actually could check that to see if your calculations are correct, why your method of calculating Ka is correct. So therefore, effective lateral earth pressures at point 0, all we're doing at this point is computing pressures. We're actually not computing resultants. Z is 0, at the surface it's 0. There's no surcharge. At 6 feet at the groundwater table, the pressure is simply equal to 115 times 6. That's the effective stress. All I do is I take that effective stress, multiply it by 0.374, the active earth pressure coefficient, and I get a lateral pressure at the groundwater table of 258.1 psf. Then I compute effective stress at the bottom of the wall at 1381, multiply that by 0.374 and get 516.6 psf. And those are all diagrammed in the on the right in A. Now, if you were to compute the resultants, my suggestion to you would be to do the following: is to compute the resultant force based on this triangle, and then compute the resultant force based on this triangle, and then compute, and those results will be a third of the way from the bottom of each triangle, here and here, and then compute the resultant force of this rectangle, and the resultant force will be in the middle of that rectangle. Now, hydrostatic pressure, since there is no compensating, at 0 and 6 feet, down to 6 feet, there is no hydrostatic pressure. Hydrostatic pressure from 6 to 18 is there's 12 feet deep at 12 feet deep of water here on the soil side. 12 feet times 62.4 is 748.8. Lateral water, the KW, if you insist on doing is unity. As I said, fluids exert the same, by Pascal's law, exert the same pressure in all directions, 748.8. So therefore, the forces on the wall are equal to this plus this plus that. And the resultant of that will be a third of the way from the bottom along there. And then those are the total forces we can actually compute. If we know all those, we can actually even compute the moment on the wall at the bottom. And we'll talk about that more in detail when we get into foundations. This is from your FE exam. I would strongly suggest that you study this carefully. This is a nice presentation of it. For the FE exam, generally speaking, the Rankine, the lateral forces are restricted to Rankine with obviously delta is equal to 0, no cohesion, and level backfill. And those are the formulas which we have for those. And we've seen those before. Again, you've got vertical stress profiles. One of the things this emphasizes, this is important, is that if you have water, if you've got any water on the if you've got, your vertical stress drives your horizontal stress up to a point. Notice actually that arrow would probably best pointing to this. They're assuming that we have an unbalanced force. This is an unbalanced condition. In other words, basically, in vertical stress, you simply take the vertical stress, minus pore water pressure is equal to effective vertical stress. Total stress minus pore vertical effective vertical stress. Okay, we've been through that. Now, the horizontal is likewise is vertical. Now, if the water level is the same on both sides of the wall, then we don't count this pore water pressure. That's why this is only counted if it's an unbalanced force. The effective vertical stress is over here. If you have a surcharge, that surcharge basically shifts the effective stress over by the amount of, and that's a uniform surcharge, by the way. They're only assuming a uniform surcharge. They're not getting into the Boost and S things. Uniform surcharge here, and then the vertical effective stresses are all shifted over. And then you would take those, multiply those by Ka, and get the soil pressures. And then if you need to add the pore water pressure back for unbalanced, you can do that. Unbalanced hydrostatic forces are very important in many different applications. Tidal, for example, you've got a 3-foot variation in tide. It's unlikely that the water on their soil side is going to drop 3 feet, and then with every tide, particularly if on the Atlantic side where you've got high tides twice a day and low tides twice a day, you only have once a day in the Gulf. It's unlikely it's going to drop, so you're going to have an unbalanced hydrostatic force in that region. And then we talked about drawdown situations such as we have with, we talked with the slope stability, we talked about those. Last, or the other additional force. Up to this point, we've talked about the main forces on a retaining wall are earth pressures. Those earth pressures can be are usually by the self-weight of the soil, and that's what we've talked about. Then we had hydrostatic pressures by the weight of the water. Now we're going to talk about loading that is induced by whatever we might want to put on top of the soil next to the retaining wall. And next is a very broad term. It is very seldom that books really get into how we figured this out. The origin of these, which is goes back to the 1930s, and it's and it was largely to the experiments of a very well-known geotechnical engineer named Spangler. And basically what he did was he actually did loaded walls and whatnot. And basically what he discovered was that there were two competing theories at the time, one based on Coulomb theory and one based on theory of elasticity. The theory of elasticity was a better way of predicting if you apply the loads, for example, like this, we have a line load. It was a better way of predicting it than to use Coulomb theory. And it's been pretty much the rule ever since. There's some controversy around it, like so many things in soil mechanics, but basically Voigt shows us how these equations came to be. Let's assume we have two line loads. And let's assume that they are equidistant from, in other words, F on the right is at plus X from the Z-axis, and F on the left is minus Z. We would get two line loads. They would give us a set of vertical stresses, but they also give us horizontal stresses, as we saw back in Boussinesq theory. And we didn't use horizontal stresses very much in Boussinesq theory. But at any point along that axis Z, and I want you to concentrate on that axis Z. I'm looking at this figure 30.5, which is actually in the upper, on the left side. At any point along that Z-axis in the middle, the stress is equal to in both cases, the horizontal stresses are in the same direction. They're both compressive. The stresses along that axis at any point, if those two F's are identical, are simply going to be the stress from the left plus the stress from right, because this is elastic theory. We have superposition, therefore they will be the same. And as a result of that, the stress at any point along that axis is going to be double what the stress would be if only one load was being applied by superposition. So what you do, the logic is, if you take basically the left-hand side of the soil away and put a rigid, unyielding wall, there's those rigid, unyielding walls coming back to haunt us, you will get the same result that you would if you had a mirrored load because of static equilibrium. And that's basically the basis for the theory which Voigt shows for line loads. I'm using line loads as an illustration. The concept works exactly the same if we're using point loads, strip loads, whatever. Line loads are very convenient because they can be used to simulate railroad tracks. And in a crunch, if you want something really quick and dirty, you could take a roadway and concentrate it at a line load. Do it that way. That's an acceptable way of doing it. It's conservative, of course. So that's how they comes up with the equations he does. The equations that we actually use are a little different, and they're shown in this. This is from your, and they were modified by experiment, as Terzaghi noted in a well-known paper on anchored walls in the 1950s. Actually note that they're different. This also shows you the location of the resultant. It shows you that for different cases, actually, as the loads approach the wall, experimenters changed how they, modified the equations. Actually, if you look at the line load, for that m bar is equal to greater than 0.4, which basically means that the location is greater than 40% of the wall height, the equations are identical. And they show you that. They also, for hand calculations of walls, resultants were to concentrate the load in the resultant was very common. For computers, they would do a distribution. The one exception to this, all this, in terms of theory of elasticity, is that uniform surcharge. And as I mentioned before, and this is exactly the same as in that slide from the FE exam thing, the uniform surcharge is equal to the pressure due to the is equal to the uniform surcharge pressure times whatever lateral earth pressure coefficient is appropriate. Whether it's active, usually it's active. Occasionally it might be. Occasionally it might be at rest. Passive. Surcharging a passive load is not a bad idea, but you don't see it very often. Okay, now we're going to get into the very last topic of the course, and that is the effects of earthquake loading. If there's one thing that has changed more than anything else in the geotechnical engineering, it is a heightened awareness and provision for seismic loading. We haven't had, for example, we haven't had the bigger, but we had some pretty big ones. And earthquakes are highly destructive events. And in our case, in the situation in this part of the country, we have to watch the New Madrid fault, because even though the New Madrid fault doesn't go off very often, when it does, it's very nasty because there's very little to stop the waves from earthquake fault to actually propagate throughout the eastern United States. So how do we deal with this? There are many methods in use, some of which require computer software, and some of which, a few of the older ones don't. Many of the newer ones do require computer software. One that doesn't, or at least doesn't to the extent that it could, is the Mononobe Okabe procedure. This was developed back in Japan in the 1920s. Japan is a country which has been interested in earthquakes for a long time. For obvious reason, the Fukushima earthquake is just the latest example of that. It tends to be conservative. It's a pseudo-static method. Civil engineers, and I always ride civil engineers about this, maybe I shouldn't, generally speaking, panic when confronted with stuff that moves. Civil engineers are trained to put things in place that don't go anywhere. And that's their job. But unfortunately, stuff does go somewhere every now and then. And so therefore, they need to be prepared for that to some degree. So what Mononobe Okabe does is, instead of trying to dynamically model and require them to get out their dynamics textbooks and freak out, it basically says, we're going to take this earthquake load and we're going to have an equivalent static load. although newer methods are coming into use, it's still the standard method. It's not the greatest, but it's conservative and it's worked fairly well over the years. Assumptions. The wall is free to yield sufficiently and with full soil strength. In other words, you remember way back in the early part of this slide I set in this presentation, we talked about the fact that it takes some movement to fully develop the active conditions, or for that matter, the passive conditions. So the wall is free to yield sufficiently. And the backfill is completely above or completely below the water table. Backfill is cohesionless. This is not for cohesive backfill. The top surface is planar. It doesn't necessarily have to be horizontal, but it has to be planar. Any surcharge is uniform and covers the entire surface of the soil waves, and liquefaction is not a problem. So those are the assumptions behind this method. The governing equations are essentially an expansion of Coulomb theory. And again, you'll note the formulas. A couple of things I would note about these equations. First, the next slide will show the we'll show the nomenclature for it. Again, anytime you're presented with an equation for, particularly for any kind of Coulomb or Coulomb-related KAE, or in this case a KPE or KA or KP, keep in mind that you need to have accompanying that a diagram that shows you what's what. The second of all is the big change between this and Coulomb theory is the seismic inertia. And by the way, just as a note, this should be arctangent of KH over 1 minus KV, not just tangent of it. It should be tangent minus 1 of K is the seismic inertia angle. The seismic inertia angle basically allows us to insert the seismic conditions into Coulomb theory without a major disruption. And of course, we also pick up the effects, and the two effects of that is the vertical acceleration in G's that we anticipate, and the horizontal acceleration in G, which is KH and KV. And KV also makes a reappearance in the forces. You'll see there KV there and KV there. So keep that in mind. Also, again, use the nomenclature that you have in this one. And it shows you there is your psi, tangent minus 1 of KH over 1 minus KV, the seismic inertia angle. This material is largely from a book called The Seismic Design of Waterfront Retaining Structures, which was put out by the Corps of Engineers in the early 1990s. It remains an excellent reference for soil mechanics of lateral earth pressures in general and seismic design in particular. Okay, if we get rid of KV, which is a common, we ignore K, the vertical cases, which are, not always entirely relevant. Earthquake waves have both a horizontal and vertical component to them, and that's where we get into transverse waves and all this good stuff. We normally, for lateral earth pressures, KV is not entirely of interest to us, but so frequently we drop that. If we drop out delta, which really actually reduces it to Rankine type of case, if we drop, if theta we can drop for vertical walls, which is particularly relevant for sheet pile walls, for marine, we get down to the KE and AE and KP down to this, where the psi angle is simply the arctangent of the horizontal acceleration. And the PAE and PPE are the same as they are, basically the same as they are with non-earthquake. There are a few observations I'd like to make. As the seismic inertia angle equals the values of Ka, Kp approach each other, they come very close. If for a vertical wall, if psi is equal to phi, they're identical. The locations of PAE and PE are not given by the analysis. Generally speaking, to cut to the chase on this, we normally use the 1/3 assumption for triangles. And if we've got, other things, we would the half assumption for rectangles if we have it. But normally speaking, we stick with the 1/3 assumption for for a lot of work we do. There are also some other things that we look at, and you can read those as well. But I want to get an active example, an active earth pressure example. We have a wall, another one of those 20-foot high retaining walls. That's where I got all these, by the way. It was seismic design of waterfront retaining structures. V is 30 degrees, delta is equal to 3 degrees, beta is 6. It's a vertical wall. KH is equal to 0.1, and KV is 0.06. So these are in G's. That means they are dimensionless. They are in G's. That means that they are the ratio of the actual acceleration in feet per second squared or meters per second squared divided by the acceleration due to gravity. And you're supposed to compute KAP and the alpha. And I'm not, like I said, I'm not emphasizing the alpha. I'm looking more at KAE and PAE. Well, in both cases, it's plug and chug. We start with the psi, which is the tangent, is the arctangent of 0.01 over 1 minus 0.067 is equal to 6.12 degrees. The KAE is, then you just plug and chug that, and you get a 0.4268. You should probably see if that works. If you're setting up a spreadsheet for it, you should set that up and see if it works for you. And PAE is simply the same formula. Notice that in this particular case, since you're given a KV enters into the PAE equation. Keep that in mind. If you are given a KV, it will affect PAE as well as KAE. It affects them both. At that point, we're done with lateral earth pressures. I know this has been a fairly long treatment of the subject. This is a very important topic, and this also actually is the last in the soil mechanics course. So, thank you.